Effects on turning circle and stopping distance. Another effect of shallow water is considered to be the difference in a vessel's turning circle. The diameter of a ship's turn varies with several factors, and water depth is one of them. Water depth plays a big role when it comes to the maneuvering of a ship in general, and if neglected, it can give wrong interpretations. The rate of turn depends on the ship's directional stability, and though the rate does increase at first upon leaving the deep water, it decreases as the shallower water is reached. These changes in the rate of a turn are comparatively small to be perceived by the person maneuvering the ship, but in combination with the speed loss in the turn, as the under-keel clearance decreases, it results in an increase in the ship's turning circle diameter. When a ship is turning, a large portion of the water that initially, on a steady ship, was relatively moving along the sides and under the hull in a fore and aft direction is now moving from one side of the hull to the other, passing under the keel. The resistance to this flow increases with reducing water depths as flow under the keel becomes more restricted, a similar effect to how bow cushion acts on the bow. Because of this, the vessel requires far greater rudder angles to turn and will only achieve rates of turn that are significantly slower than normal, with turning radii that are much larger than what the same vessel experiences in deep water. The latter effect is also accentuated by squat. As a ship moves into shallower water, it starts to suffer squat and interaction with seabed features lying to one side or the other of the ship's course. Squat in very shallow water will significantly increase both the trim and its effects upon a ship's steering characteristics, as the greatly reduced hull clearance further restricts the water flow under the deeper end of the hull. Due to the greater pressure of the water aft and around amidships caused by the restricted water flow below the vessel, the pivot point of the vessel will move aft, and if the vessel trims by stern due to squat, the pivot point will move even further. Unlike the situation in deep water, where the center of the main turning force caused by the water resistance is located forward of the LCG, longitudinal center of gravity, causing the ship to turn further when it starts turning, in shallow water this point may move aft of G and cause the opposite effect. That is, the hull would actually act against the turning moment of the rudder. In this situation, the ship will become almost impossible to steer by the rudder and behave as if it is almost running along train tracks, dictated by the seabed features. Due to the center of hull resistance moving aft, the pivot point of the vessel also shifts aft, and as a consequence, the rudder will have a shorter lever and thus reduced effect. When a ship moves through the water, a portion of the power required to affect the movement is used in setting the water in motion. The water in the boundary layer around the ship is either totally or partially dragged with the vessel, and the vertical rotation motion is locked up in the wave system that is caused by the ship and moves along with it. The movement causes a mass of moving water, which effectively increases the ship's inertia. As can be seen in a standard wheelhouse poster or maneuvering booklet, the larger the vessel's displacement, the longer it takes for a vessel to stop, both in terms of time and distance. The increased inertia, which in this case is caused by the moving water, will result in a longer stopping distance.